All right. It's good. It's better. Okay. Thank you for coming and taking your time to listen to me today. I'm going to talk about something very simple, because as Rami mentioned, innovation in the circuits field is kind of tough, but we would use and utilize something that everybody understands and appreciates, which is the analogies. As long as you know the fundamentals, using analogies, we may end up with something new easily. And there's a science behind it. So it's called a design by analogy, or analogy-based design. There are different terminologies for it. Mainly psychologists, cognitive psychologists are kind of researching on it, and the industrial engineers and the mechanical engineers are kind of using to come up with something new, and also mainly chemical engineers and chemistry people are using analogies in their teaching, and not many circuit guys are using analogies to teach stuff. And in my teaching, I typically use analogies to really explain analog circuits or principles, which some of the designs that we have in my group is based on that analogical approach sometimes, because most of the time we deal with very fundamental stuff, okay, in analog circuits and the systems, and we can relate real life experiences of people with the circuit design, and that is kind of gives us into a design by analogy approach. And based on that, the analogical approach, we developed some technologies we call the supply boosting technique, which differentiate itself from other boosting techniques a little bit, and we have some applications of that developed technique using comparators, ADCs, and eventually use that for ultra low power CMOS image sensors. And all this development of supply boosting and others are kind of had a purpose in general, because we would like to actually design self-powered image sensors. And to do that, you have to think out of the box a little bit, and the analogies are typically the one that get you there. Okay, so I'm going to kind of cover those, how we approach and come up with that, and use it in real, and what the outcome of that research is. And by definition, you know, Merriam-Webster says that the analogy is a comparison of two otherwise unlikely things based on the resemblance on a particular aspect. Mainly we use it similarity of two different domain characteristics, so that we can relate things much easier. Okay, and obviously we use the analogies a lot in many aspects in our life to really explain things simply to the people higher up most of the time. So and or very juniors who does not really understand the big concepts that we are kind of dealing with in engineering domain. So design by analogy, as I mentioned, is the one that cognitive scientists have been investigating for many years to develop some kind of a methodology to increase the creativity of the groups and the companies and the people. They use this new solutions or generate these new solutions in target domain, mainly in this case is the circuit design domain, based on the inspiration drawn from a source domain, some other that you can take from life or society or in nature. And obviously they have to have very fundamental understanding of both to be able to make this cross-domain reasoning and analogically relate those two issues. And generally, cognitive scientists are kind of dealing with this new idea generation, design by analogy. And design by analogy, actually, one of this idea generation methodologies that they were investigating, like brainstorming. Everybody knows brainstorming, how you get together and then try to explain or attack a problem. Design by analogy or analogy-based design is one of them. And it's almost 300 different approaches exist. And especially patentable ideas are typically come from the analogical reasoning. And because patentable ideas or patented ideas are typically novel, non-obvious, and useful. And 80% of the patented ideas written on those patent documents are not published. You cannot find it anywhere else. So most of the old guys go and read the old patents, go back all the way to the Tesla to look at what the guy is thinking about, or some other guys who invented some other stuff that they can relate that technology into their problem of today, okay? One of the important issues that kind of block us from coming up with new ideas is so-called design fixation. You know something and you cannot think out of the box because of that, okay? And you would like to stay in your comfort zone when you're designing something and you don't wanna try something else, okay? And by analogy, which you use some other domain that everybody kind of familiar with and use that to be able to get everybody talk about it, and then use that to really bring that to your fundamental problem, okay? And also it improves the ideation process, and also it facilitates interdisciplinary contribution, okay? Because if you bring different disciplines in together, sometimes difficult to get them attack the same problem. So by using the analogy and analogy domain that everybody knows and appreciates to relate their experience and their knowledge to bring that through the analogy to other domains, okay? And the main approach of design by analogy is the assumptions that similar problems can be solved by similar solutions from different domains, okay? So I'm going to show you how did we come up with that supply boosting technique, what it differentiates from the other stuff. And obviously analogy we have been using in different teaching settings, and so that we can be able to simplify the complex stuff, okay? And relate the knowledge that a junior student knows, and bring that to the context that we are teaching circuits, and using analogies, you can be able to maintain the knowledge longer, because again, remembering the certain equations is not possible, but remembering some analogies from your real life is easy. So you can relate and maintain the knowledge longer. And also gives a different perspective for students to really look at the things a little bit differently. When we teach something, it became very complicated for people who don't know anything about it. But when you simplify it through analogies, you can break that barrier of scare, right? So that they can approach things more freely, okay? The problem is, it's a double-edged sword. It's not, because you're trying to relate something in different domains to engineering problem. And it's important to know really what that limitation is on each domain when you relate stuff, because what you say is not that important, they say. Well, how it is perceived is more important than what you say, right? And people have their perception based on their background. And so you have to be very careful when you're constructing these analogies, when you are relating to real engineering problems or knowledge, okay? I'm not an expert in this field. I'm not a cognitive scientist, but I know how to use these analogies on my teaching and or research, okay? Obviously, we all know fundamental analogy that we always use when we talk about the electric currents, right? And or resistance through a system, like the potential energy of that water is going to create some kind of a difference, and that difference can be used to move that current from high potential to low potential, right? Like the voltage that we have, or size of that pipe that you are draining that water is going to change the amount of current that you are draining through that pipe, which you can relate to the current, or construction of that pipe is going to create some kind of a resistance for that water to move in the same cross-sectional area. You're going to have less current or power. We also use the raindrops for relating the photon and imaging. In general, we treat photons as the particle of energy and use the trajectory of those photons reflected from different places to collect it in different buckets of which we call the pixels, to collect those photons coming from different locations. Okay, and in general, powering or operating our electric circuits and systems resembles how we distribute the power, the water in our daily use in networks, water networks, water mains, and always you have to have some kind of a water source that you place it in somewhere, and then you distribute that in a controlled fashion. And using some kind of a regulator and switch, you can be able to use that water volume and the pressure to be able to do some job, okay? And at the end, you close the loop, water cycle to dump that water to ground to let it circulate. Similarly, we have the main power that we have, that we distribute and manage that power, and provide as a voltage and the power to our circuits. And at the end, that current is going to be closing the loop through the ground port of the system. So, and there are certain assumptions that we have for this, or desires that we have for our system, as the power is unlimited. And most of the situations, we assume that power is somewhere, okay? and somehow managed and distributed, and we always have that main voltage constant. In reality, it is not, but the power and the voltage is regulated and provided to our systems, and our systems and circuits are going to process that input signal, generating the output. Similarly, water pressure and the water volume that you provide for doing a job is considered to be constant and get the job done. And typically, we don't really care about when you are really learning how to design those circuits or unaware of that this power and the voltage there is constant. Okay. Powering and operating typical analog circuit is kind of interesting. Almost all circuits that you know, learned, or we teach have power that is continuously provided, and that power is typically biasing our circuits in a class A fashion, and the signal is passed through. In class A fashion, if you look at this simple common source amplifier, typically we care about this block, which is the amplifier, right? But this is not just an amplifier. This has some other elements that consume power, okay? And there are other elements that we use to couple signals in and out, okay? And most of the time, we really don't care about this biasing or others, and we just focus on teaching this main amplifier block, okay? And typically, when you are operating these circuits that you learn, we make sure that we have a gain element, which you have to bias that gain element, either in an amplifier stage in this example, or in a power distribution system. That element has to be biased properly, okay? And most of the time we bias, for example, in this case, this transistor in saturation, okay? And what saturation requires is that you have to constantly pass a current through this device. Even though you have an input or no input, that current has to be passing through. And always you have to have some kind of a supporting elements and or electronics to really provide this transistor to work properly, okay? We say that's proper operation, keep it in saturation region, and apply the signal across that. And in average, that current is going to be always passing, and that current is going to change that IO range and the characteristics of that transistor to make sure that signal is passing without clipping. And most of the time, this operation style, which is a class A operation, is not power efficient, okay? If you really analyze how much power that can deliver to the load, you end up with less than 25% or maximum 25%, but you never reach to that level. And it depends on the input level and also bias this transistor, and you always end up with less than 10%. So 90% of the power is going to be not used or wasted. Like you're running a shower head, okay? And you are not getting in the shower, okay? So you are wasting the power all the time. Unless you get in the shower, you're not going to use that water effectively, okay? So that brings us to that showering situation, okay? So, and that's the main analogy that I can build, that as long as I have a main power source or the water source that provides me an infinite amount of water using a switch, I can be able to provide that water to my shower so that I can have a constant volume and pressure, and the pressure and the volume I can control with that switch or regulator. That's the same as what we do. If you have a power source, you have to use some kind of a regulator, and most of the time you need to have some kind of a sensor to make sure that regulator works in the range of operation, okay? It's same as the switch, and that you can control. And obviously, somebody has to operate that switch, right? And that somebody is, since you are the one who is using it, to take the shower happily, right? In a constant pressure and the voltage as a load on that system, you are going to control that switch to operate. So intelligence is inside, but there is no intelligence here. Only the intelligence comes from the sensor side, okay? That provides that intelligence to operate. Or in most of the case, we have some kind of a storage tank that we hold the water in, okay? Then use this, again, switch to regulate, and depending on the size of that storage tank and how much that we turn on that switch and or regulate, we can assume that the pressure is going to be constant, okay? And obviously, if you try to model this, you may have some kind of a supercapacitor that you can have the charge stored when the water is turned off or the power is turned off. You can feed your system with that supercapacitor, or you may have some kind of a rechargeable battery without any water main that you can provide your load to a sustaining power and voltage, okay? Obviously, as this drain down, or the rechargeable battery or the supercapacitor is drained down without the main input power, you're going to see that your power output is going to be reducing, or the voltage is going to drop, and to maintain the water, and or your pressure is going to drop, while your volume is going to drop also when the tank is drained. Now, obviously, you can put some intelligence in it, in your water system, maybe a floating ball that you have in your toilet bowls that controls the amount of, or the level of that storage tank after it drains or not drains, or you can have a certain level that you can set through that bowl. But on electronic side, you have to have lots of things, okay? Obviously, even though in mechanical systems or water system, you have a very simple fixture, in electronics, you have to have some kind of an intelligence, okay? That intelligence has to be supported by some electronics. And you have to have a closed loop. You may have some kind of a boosting or blocking the power that you are bringing from either the main source or the rechargeable battery, or some kind of a charge pump to be able to generate that almost constant voltage and current. Or you can hire somebody, right, and have a replenishing source from somewhere, either a well or a river or some other place that unhappy guy has to fill in your tank when the water drops to a certain level to maintain the pressure and the volume of that water. And obviously, we call that as an energy harvesting in electronic design, where you use lights or any kind of environmental source to generate that or harvest that and boost or charge pump that up and regulate to deliver the load. Again, even that energy harvesting requires some kind of an intelligence, which all these blocks are going to use and waste power. And as a result, you may not really truly self-powered system, okay? And you can see this, depending on this shower head, you may reduce and lose some water, but in general, on the system level, from water main to the shower head, you're not going to have too much of a loss, especially in this case. you have an intelligence that controls that level, which is going to maintain that water pressure and volume on that shower head. Only in this case where you are doing the energy harvesting or ask somebody to bring that water. If you're in military, right, you can ask the guys to bring the water, and then you do the shower as an officer. But in general, we end up with less loss here. But in electronics, we have lots of supporting electronics, and we end up with losing too much of a power on those supporting electronics. And most of the time, they say, okay, they have a converter or an IC that has 97% effective or efficient. But if you really look at the data sheet and try to operate it, you see that at different regime, it drops to 20%, 50% or less, even not including some other supporting electronics that they have in there. Just mention that they have just 97% of efficiency in that domain. So, especially in energy limited situations in IoT devices, you cannot deal with this much of an intelligence and loss in the power that you harvest in the environment. Okay, so what do we do? One way to approach this is to design ultra low power electronics. Okay, for especially self-power systems, and we can build an analogy from our experience. What I was thinking when I was designing this self-powered image sensor is to use my own background, right? What I feel, what I live, what I went through. I went through the big 1990s Istanbul drought when I was a university student. The dormitory, we cannot be able to have the water to drink, water to shower. So we have to have come up with a solution, right? And what we are typically doing, obviously you can go ahead and buy a bottled water, but you can only bottled water, you can use the bottled water for drinking, or time to time we were hearing sound that the water is coming, because when they turn on the water for 1 hour at the midnight or something, so you can hear it and then you run for it and fill out your bottled water. But obviously you need to take a shower, and we were investigating that time how much water that we need to take a shower, right? And we end up with about 4 liters or 1.1 gallon of water is sufficient enough, which is 2 liter bottles. So what we do is we get the bottled water, open a hole on the top, right, to get a shower. So and when the water comes, we fill it out, clean one again, and then we heat them up on the panel radiators, so that in the winter you have a sufficient water to take a shower. And you have to be obviously mindful about how you use that water. Careful and organized. You have to be very organized and mindful about your water source. And obviously the key thing is don't use all the water. If you are not organized, you end up with, at the middle of your shower, you end up with no water, and then you are shouting your friend to bring you some more bottles to take a shower. So the key here is obviously, and the idea that we use in camping situations, right? You can buy this picture of this unit, which holds 5 gallons of water, and shower head. You can heat it up by hanging in the sun and take a shower, or use other purposes. It's the same idea in energy limited situations. It's like a battery. But the key here is, here we didn't really care about the pressure of the water or the volume of the water that you are using. For every time that you are using to wash some place of your body, that you put the soap on, so every time you flip it, you have to do a job, okay? And complete the job effectively, okay? So for every pour, you have to get something done. It's like a clocking system, okay? And again, you do not care about the pressure drop when you use it, or the volume that you are, well, volume you may care, but the pressure you don't really care, okay? For every job, you have to have certain volume of water that you need to use. So this is the main idea that we start building this technique. As long as you finish the job that you set to do before your resource is running out, you are okay. Okay. So that brings us to a supply boosting technique, where typical boosting approaches for powering a system is you have a clock which runs higher frequency than your operating frequency. It doesn't have to be this circuit doesn't have to be a clock one. It can be an analog one, but you have to have some kind of a circuit that is clocked faster than the bandwidth of your circuit operation, and be able to maintain this voltage level constant, okay? Like the power and the volume, you try to maintain the same level by burning some power here, wasting power actually, and you have to operate your circuit at lower speed than your clocking speed of that power generation system. Okay, so that's a standard approach. But what we are saying is that if I boost this voltage, okay, double the system supply voltage once, like pouring once, okay, I don't really care about that voltage drop. As long as that is higher than the reference level, and if I finish my job before that, I don't really care about this drop, okay? So I don't really need to maintain this level all the time in this 10 millivolt range of that VAD level, okay? So that brings us to an approach we call actually we should call it one-shot supply boosting, but we call it supply boosting technique, where we have a circuit that boosts the supply voltage higher, okay, and then let that voltage to drop, okay, and get our signal pass through our circuit, okay. Like you have a shower head, right? Runs and stops, runs and stops. So you need to get under it when it's running and then get out of it or stay there to get the job done. And or you can have, if you have a clocked system, obviously, you may boost that clock also for that system and power it through the same boosted supply voltage to maintain that, for example, switches to on all the time, okay? So we call this supply and clock boosting technique, or the circuit that manages this, the supply and clock boosting element. And obviously you need to come up with that circuit. But there are certain issues that you need to deal with. Obviously, you cannot use the 5, for example, if you have a 5-volt process that you have, you cannot really increase that voltage to 10 volt. It breaks down at 5.5 volt because it has a breakdown level, or the maximum supply voltage that you can use in that situation. So instead of a 5-volt process supply level, you can end up with a system supply voltage level much lower, at least twice lower than the process supply level, like 1.2 volts. So maximum voltage that you end up with in the circuit is going to be twice that, still less than 5. Okay, and you can raise this system supply level to 2.5 volt or 2.6 volts so that you don't create a breakdown. And why choose and like 0.5 micron old technology, comparing with using a 22 nanometer process or 90 nanometer process, is the leakage.
Low leakage.
Again, you have to have mindful about your leakage, right? And all analog processes and most of the power management systems that you or ICs that you are buying are very old processes. They are not like 22 nanometer, 90 nanometer processes, okay? TI still maintains the 0.5, 0.8 micron technology fabs in their infrastructure to be able to produce this low leakage element, okay? So this is the same idea. As long as you don't really go over that level of process supply, you are okay to use this technique. You can come up with other questions like, okay, these process elements are designed for 5-volt operation. You are operating this or simulating this circuit at 2.4 volt maximum. Would the model support this? Is a question. Even that process guys may not really answer that question. They say, okay, this is, we are giving you a 5-volt process, use the supply 5-volt. Don't go 10% up or down, we cannot guarantee. And their model may not really support that also. So you have to be very careful about the process that you are using and the simulation models that you are doing the design. Obviously, as I said, you can use pure analog operations too. Like level shifting is one of the most power efficient operation that you can have. As long as you make sure that you have used low current levels, you can be able to buffer signals through simple electronics very fast. Avoid the op-amps, but use simple level shifters of CMOS. Okay? And obviously, this supply and clock booster circuit has to be very simple, low power, and low leakage. Okay, and we know and use that in especially clocked systems. And this is the circuit is well known and used to boost the clock in mixed signal circuits, so that you can be able to turn on and off a switch effectively. And here, it's a very simple circuit that has a supply boosted voltage and the boost clock level, where for clock being 0, you end up with boosting or charging this capacitor to a VAE level. And then when your clock is high, your supply output or the boosted supply is going to go approximately twice the supply level that you charge your capacitor up, and similarly, boosted clock is going to go from VA to twice the VA, and 0 to twice the VA, but your VA boosted value is going to VA to twice the VA. Okay, and depending on your load on the boosted supply output, you are going to see a drop. That's why your circuit that you are loading this is going to control the amount of discharge that you're going to see. If you don't use the M3, for example, in this circuit, you're going to see this voltage to drop indefinitely until you switch to charging mode. Okay? And here you don't really need to have a regulator, no LDO, nothing needs. As long as you get your signal operated or signal pass through your electronics here before it drops to the A level or it goes down to the A level, you are going to be okay. Okay. Now, obviously, again, for analog signals, it's kind of, you're going to see this drop on your analog signal passing through. But again, if the operation is short time before it drops too much, it's going to be okay. And obviously, you can have an inverse version to drive the CMOS switches with the same idea, same holding capacitor, and be able to generate a logic inverse version of that clock signal. And here is the first comparator, which is a clocked system that we come up with. Here, obviously, this is the supply and clock booster that generates this boosted voltage, and from this supply level, and also we have the boosted clock, and we have the bias generator, which you provide this bias current and mirror it so that you can have a level shifted analog signals applied to your latched comparator with switches that is turned on and off using the boosted levels. And then you have a second stage of a comparator that kind of operate at supply level to be able to generate that digital out. And from input to the output, again, you have to maintain the DC currents or make sure that you do not consume too much power from this holding capacitor to be able to generate that output. Here's a simple simulation that, again, C5 process, threshold voltage of NMOS is 0.8, and supply level is 1.2, so the double the supply level, you end up with 2.4 volt. And this is the first stage output that you have here. And you generate some kind of a difference of here, the input common mode voltage is 1 volt, and you have a positive 0.25 millivolts. And since the supply voltage is 2.4, and you are kind of level shifted the signals up with a ultra low power consumption there, that cause this voltage to drop, and everything is going to drop with it too. But since you are getting things done in maybe 6 microseconds or so, second stage output is going to be able to make a decision with the difference that you have at that point to generate that decision. And from this point on, you don't really care. You don't need to regulate that voltage and go do something else, change the input, and generate 0 in this case, where you have a negative 0.25 millivolt of an input. And obviously, this is going to give you larger input range because you are level shifting input to the second stage or the first latch comparator, and be able to generate that difference. Again, here I don't really care about this drop. Obviously, you don't want it to drop very fast, even though it drops very fast. Depending on where this decision or transition starts, you may end up with a larger and larger difference that is going to have for that too, and you are going to be able to generate this signal no matter what. The precision may drop, but still you can be able to make a decision. Okay. And obviously, to be able to make this happen, you have to have a large boosting capacitor, maybe as large as the circuit that you are going to build. This is a 2-poly 3-metal process that you can have polycap, but again, your circuit might be as big as the boosting capacitor. In other situations, you may want to use the space that we use, the decoupling caps for boosting as a boosting capacitor in your supply boosted system. Now we said, okay, if this is working, then we can build an ADC out of it. but you need to know what the precision is, what the input range is for different supply levels. And this is again C5, 5-volt process. You can operate this circuit down to 0.85 volt of a supply level. Okay, and you can have a battery that starts with 1.2 and at 1.1 and 1 volt, a standard coin batteries, and beyond that, no system works, but this circuit can work even for 0.85 volt, which almost depleted that coin battery. Obviously, there are things that you need to pay, which is the input range. You have to be mindful about that and use this for different situations. And this is, again, we built this, fabricated, and measure the precision, measure the resolution that we built before we go to the next to build the ADC out of it. But before that, obviously, every first version has a second version that you see. And here we have the second version that instead of using a second latched comparator, we come up with a solution that kind of speeds up this operation 100 times almost, which is good. Sometimes this is unintuitive, but somehow we come up with this approach. Instead of a second stage of latched comparator, we just use a level shifter again. Okay, and then use this node and this elements to be able to make a decision much faster here, unloading this first stage and getting this to decide much faster. Okay, and the rest are the same. So, and we end up with measuring and using this in standard SAR ADC, where we have again that boosted buffer that generates inverted and non-inverted clock for our switches. And we don't have much switches here. We have this, and inside we have some, but those are connecting the either reference level or the bottom or the ground level, so that you don't really need to have too much of a buffering there. But we have the supply boost comparator there, and the sample switch also has that boosted buffer. We fabricated simple timing, and we end up with proving that we can have some energy efficient operation at lower, well, it can work down to 20 kilosample per second with a 3 microwatt of power. And mainly, this is a dynamic power, not much of an analog power, the DC power circuit power that we consume, because you are operating at certain clock frequencies for those capacitors to charge up and down. So the dynamic power consumption is going to be the major issue. And again, this gives us fairly competitive figure of merit with this new approach, and decided to use this one into self-powered image sensor. Okay. Again, all these ideas are generated to support our vision of self-powered sensors, image sensors. And obviously, we put all those into, and also we develop a readout technique for image sensors using a boosted supply, boosted reset, and boosted select, okay, which might be another talk. Or if you have time, I have the slides I can show you. Take some time to explain that. But we put it in there. We have the supply boosted ADC. We have a global amplifier, column sample and holds, and use very power efficient shift register based decoders. And also we have some on-chip DACs and stuff that you can bias them in very low power. And obviously here we have this supply boosting capacitor of 166 femtopicofarad, which is huge in other processes. But you can see that there are lots of empty space around, which we didn't utilize to avoid noise. But we end up with just proving the idea that supply boosting on an image sensor that can produce an image that is meaningful and low power operation is possible. And obviously we come up with other technologies like energy harvesting and imaging pixel, where in the pixel you can generate both power, like operating a photodiode in solar mode, generate the power, flip it, and then use as a photodiode photosensitive element. And we also have other elements that I'm not showing here that has a charge pump to harvest that energy and feed it back to our circuit. And here is the imaging mode operation. Here we have the supply boosting that we read the signal through the pixel array and be able to pass through this low power global amplifier, and we have the 10-bit supply boosted SAR ADC, which has a serial output, and be able to allow this voltage to, and that voltage obviously is provided by this to drop. Well, this one has its own supply boosting itself, which this clock is one of the reasons that we have. And as a result, we end up with 1.2 volts supply voltage running at 7.4 frame per second, consuming about 14 microwatts for the first generation of power, while we would be able to harvest the energy also, okay, through these elements. And this is the first design, kind of a proof of concept design that we published in ISSCC in 2011. Okay. That at that time, this is most power efficient and image sensor that can also harvest energy. And you need to harvest the solar energy on the focal plane about 8 seconds to produce 1 frame of or 7.4 frame of images in 1 second. So, and again, we would like to have a self-powered image sensor, but why do you need a self-powered image sensor, right? So the main idea was, if we have a self-powered image sensor, we can be able to implant in the cochlea and be able to maybe provide some sensing for the blind people. Okay, and you can read that in our investigation of the cochlear implant kind of systems. And this is the setup that we had, running everything on this battery, including that FPGA system, connect XD in a room conditions, running at 1.2 volt regulated supply. And I think this is one of the image that I take. Oops. Click it to mouse. Well, let's go to the next one now. Next one works fine. So this is the image that actually taken about 1.5 meters in room lighting conditions, where it runs at 5 frames per second consuming about 14 microwatt of power on the image sensor, including all the pads and stuff. So this is a 54 by 50 image. And for a blind people, if you ask a blind people, I'm going to implant something in your eyes, what do you need? And most of them says, I need 1 pixel. 1 pixel only so that I can be able to see the light and dark. 2 pixel or 4 pixel is a luxury for them. 54 by 50 is huge because after 32 by 32, you start seeing the intelligence in the images that you capture. Okay, and the 54 by 50 consuming 14 microwatt and harvesting that much of energy over 8 seconds is still something to be improved. And obviously, again, this is the first approach that we had, or first proof of concept. And later I have my PhD students getting the revision 2 of EHI, revision 3, revision 4. Revision 4 was achieved like 4 microwatt of power with a self-powered capability. So we improved the harvesting efficiency a lot with different techniques from that photodiodes and reduced power further with the techniques. Now, you may say, okay, why are you talking about this? Everything that we try to do in circuits, we try to address very fundamental things, okay? And most of the time, we have to come up with something that is out of the box, okay? And using analogy is one of the way to do it, okay? I have other, again, as I mentioned, I use analogies when I was talking about circuits, especially in sophomore level that I kind of start teaching stuff, because analog electronics or electronics in general perceived to be difficult topic. They don't really go into that field and come to our classes in the senior level. Okay, and having an analogy always when you are teaching is going to attract students to really think not only out of box but really understand the fundamentals, and or you can utilize this design by analogy or analogy-based design in circuits to come up with something different, new, and useful, which can be patentable also, and be able to make a difference, okay? Like in the case of the ultra-low power CMOS image sensor that my group kind of developed over the years, okay? And obviously, you have to come up with other analogies to be able to really power your electronics. Like, any ideas, any suggestions? You know? Okay.
So I love analogies too. But I was thinking, so the shower idea, the idea is that you go in when you have voltage or pressure, and if that pressure changes, you're still okay. So that didn't quite help me see the comparator circuit and why it has such good power supply rejection ratio. So if you can go back to the comparator circuit, because I think what you're saying is that even if the boosted supply voltage changes while the comparator is making a decision, it still makes the same decision, right? So
yeah.
Oh, thanks.
I mean,
hello. Yeah.
Go ahead.
So I mean, I see those waveforms, but if you can go back to the schematic and you know, you have some inputs and your output is insensitive to the fact that your boosted voltage is changing during time. Is that correct? Is that the idea?
Yeah.
So from a circuit point of view, can you say why the power supply rejection ratio is so good? I mean, it's differential pair, so that helps.
That's one thing. But again, you mean this drops, but this doesn't drop?
Yeah. So from the schematic, why does the supply drop, but the output doesn't drop?
drop, but supply doesn't drop.
No, supply drops, right? Because you're saying that once it's boosted, during the decision-making, it's draining the capacitor. But your output still is the same, even if your supply is varying.
Because again, you have a positive feedback there that kind of locks this up in one direction. And that direction is very difficult to turn around, even though supply is dropping.
Okay.
And here, the input is negative. It already make a decision here, while the supply drops about, I don't know, 5% or something.
Right.
And there, at this point, I should point here, at this point,
So it's already tripped. It trips early. It trips.
I mean, that's the idea actually. As long as you start making a decision before it drops too much, you don't really care about it.
Yeah.
That's the idea of this boosting. And again, this can drop much faster, and still these two are going to go down, and maybe somewhere here they are going to start splitting, even though this drops maybe 20% down from the 2.4. Okay, and also your switches kind of follows the same thing, although their impedances are changing. It's not going to affect the final decision because of that positive feedback that you have. And only problem here is this loading effect that slows it down. This can go much faster and start making the decision. That's why in the second one, we reduce this decision point where the supply voltage is still sufficient.
So that's nice. The analogy I would use that, because I sometimes, shower and turn the water off to save water. And the trick is you have to clean early, because after you leave the water on for a while, it's just for fun, right?
Yeah.
So it's just, this is warm water, it feels good. I don't need it anymore. So the analogy here is the decision-making is done early in the step.
It's not like a continuous running of a shower head. You have a bottled water. You are clocking actually. You are clocking the supply. Although when you clock or flip upside down, that water level drops, but still you have some water coming. And you instead of 1 second per pour at the beginning of the bottle, in the second or at the end of it, you may need 2 seconds to have the same volume to cover the area. That's why it's important to know how fast that you need to use that water to clean things up.
But the schematic, so it's not really power supply rejection ratio.
No.
It's the feedback that makes the decision quick. It's the positive feedback that makes the decision quick.
That's the nature of, that's why we are using this latched one. Otherwise it's going to be.
Okay, thanks.
Also, the second latch is not boosted.
Yeah, because it only has this boosted this guy, and the second latch, because this voltages are right now is very high, higher than the VAA level, and since this guy's M6 and M15 are NMOS, they need higher voltages. So, and you cannot boost that voltages, and you have to use it by because the output are
I mean, it's the hard thing to see for me is just like where the transitions are. Like you started, the VO plus, you followed it, like the output, the actual output swap. Could you just follow it over time? Like VO plus is the actual answer. It's on the right, not out one, but on the far right. Go back to the schematic. Sorry about that.
Okay.
VO plus, which is on the very, very far right. It's the actual output of the system.
Yeah.
Then if you go to the plots, could you follow the VO plus over time on your plot? Because it's hard to see.
This is VO plus.
Okay.
It goes from 0 to VAA.
Yep.
When the input is positive, 0.25 millivolt difference.
Yep.
That's the delta. So, and before that, you have this second latch comparator output, VO2 and VO2 minus. which is this output.
Yep.
And you use the threshold of those C and D comparators to really make the decision at that point.
This one, when I saw this one at the beginning, but then where's the other transition? Like when it goes to 0? Like, is it hiding in this?
Yeah, I mean, this stays at the 0 level.
But it goes to 0 at 30 microseconds or at 35?
No, this always stays at 0. So the VO plus, which is this output, which is the inverted version of that, stays at 0 first.
Yep.
Pre-charge. And then during evaluation phase, if the input is positive, it flips to
I got you.
VAA.
Okay.
But if it is not, then it stays there.
Okay,
It doesn't
got it.
really change.
Okay. That answers my question. Thanks.
Okay. Any other ideas?
I have another question on slide 21. Do I talk loud enough? I mean, yeah, so you talked about the harvesting aspect. Like, where is the photo detector and how do you configure this to harvest versus?
Yeah, this is the imaging mode operation. When imaging mode, you end up with this pixel where you have two photodiodes that are in imaging mode. I didn't put the harvesting mode. In harvesting mode, this flips up, so you get this point. Well, again, this is the imaging mode where we have a switch that shorts this to ground inside the pixel. If it's an harvesting mode, there are other connections to this circuit in the pixel that generates the solar cell and that energy harvesting. There's another bus that's not shown in imaging mode that connects this to a booster that harvests the.
So we just should refer to the paper.
Yeah, the paper has everything. I have other slides I can show it also, but at this time I just want to show the imaging part where the supply boosting technique is used. Okay. Any other question?
For the additional revs that you talked about, 3 through 4, did you maintain the same pixel size array, or did you see any need to scale? I guess I'm interested in the scalability of everything, increasing the number of pixels and maintaining kind of the same architecture, the same power usage. Or
yes, I mean, this is the first version, proof of concept of an idea that is published, and then we have the second version, third version, fifth version. Stopped it. That instead of a 54 by 54, we increased to 72 by 72, 96 by 96, different versions. And even with those, we try to scale down the power consumption to less than 5 microwatt or so. And obviously, if you run it at 1 frame per second, it goes down to a couple micron of a power consumption on whole signal chain. From input to the output, and you can be able to harvest more power through those larger arrays also. So if you look at the papers, yeah, you can look at, well, this doesn't have the whole, but if you go to my website, I have all the papers listed there. That second version, second generation, fourth generation of EHI technologies have different capabilities.
Follow-up question: Do you see a limit on how large the pixel array can get? Can you get 500 by 500 pixels in that range?
You can, because you do not consume any power on the pixel array.
Okay.
Again, we have a supply boosted readout technique for the pixel array to read, and there you cannot really consume too much of a power. Main power is consumed on the pads because you have a digital output and you are driving 10, 20 picofarad of load, and typically if you read other people's papers like Sullivan, University of Michigan, they have a paper, they provide like 2 microwatt, but they don't include the pad power. So as a result, they only report this one, and maybe this one. They end up with very, very, very low power. And then you think that, oh, they have 1 microwatt image sensor running at 30 frames per second. And you say, okay, 30 frames per second, 8-bit ADC running at that frame rate, you calculate the simple pad power consumption of that chip. It's 100 times larger than what they reported. That's the problem actually in the academia, that they don't really fully disclose what they are doing, so that people try to, think that it's going to be reproducible, and it is not. So that's a main problem. And even for this paper that we published, we get a special thanks that we kind of provide all the details and all the issues in that paper, because not everybody is that truthful to say this, but so, any other question?
I guess increasing the array size, would that give more energy harvest, you can harvest more energy?
Definitely, definitely.
So because I know you increase the array size, you have to increase all the column and row decode as well. But does it result in more energy rather than more?
Yeah, you harvest more. Again, this is a proof of concept, very simple idea. I'm going to flip one of them and harvest energy, make that one larger than the other one, and then flip it back to make the imaging. So that ratio is important, and how you build that is also increase the efficiency of that energy harvesting on that pixel photodiode. And here in this, again, I have other slides for that, but for this ones, we use a simple PN junction or N plus and P substrate to build this pixel. Again, this is a proof of concept first version, and then we spent a lot of time to really improve that energy harvesting using deep NVL and ML combination and stuff to be able to increase the power harvesting efficiency to be able to make it more self-powered. So.
What is the solar cell efficiency roughly?
Well, since these are poor silicon, we end up with more than 10%.
That's good. That's great.
Is the process, is it, this is not a CIS, is it a CIS process?
No, it's not a CIS process.
So you made the diodes from just,
Regular PN junction.
so you just made the junction and used whatever you got as an imaging diode.
Yeah, the thing is, this is a C5, 0.5 micron technology. This is a FOX. It's not an STI process.
Yeah.
If it's an STI, then you can talk about the leakage on the STI, but this doesn't have an STI. That's why we stick with this, because it has a low leakage, even on the photodiode side. Even it has, well, some other people try to build energy harvesting pixel technologies. They couldn't, because they are not really careful about where the current is going, right? Or leakage is happening. If you try to use 180 nanometer with STI, try to do this, it's good luck.
What about 130?
Well, we need to look at it.
We have to wait and see.
You have to be very, very careful. Again, fundamentals are very, very important. You have to understand the fundamentals. Even though a simple PN junction, right? What would be very complicated about building a pixel, right? In theory, but if you are not careful, you cannot get anything out of it. So you have to know your fundamentals.
Do you have a number for the dark current that you got?
Yes, in the paper I have.
Okay, per area, okay. So
Yeah, I mean, I have everything. That's why we do always full disclosure. Dark
how
current.
does it compare to the regular CIS
Well, regular CIS, they have certain ways to solve that problem. They don't really report the real uncorrected process leakage. And for pixels, for CIS processes, they have this STI retreat that they avoid that dark current to leakage and stuff. So in Fox, you don't really care about that.
Any more questions either online or in the room?
So I have a question. You opted to use a dynamic approach for energy harvesting. Why would you choose that over like a static pixel, like one pixel that was like for energy harvesting and adjacent pixel for imaging? Because wouldn't the dynamic nature of it increase the power usage?
The thing is, we tried that too. Now, typically what you would like to have is have a single, we approach this like harvesting, imaging, kind of ping pong situation. Then I said a research question to my students. I said, I want all together, have harvesting and imaging at the same time on same structure, and he built it. So we could be able to, in revision 4, be able to both harvest and image at the same time without really going ping pong situation. So it's again, the first concept approach, get it working, show the world that it's working this way, and there is a room to improve, and somebody has to do that. And since we are ahead of everybody else, we could be able to really improve with different versions to the point that it can harvest and image at the same time. So it's all about the pixel design.
Thank you.
During Istanbul droughts, that's one way to do it. The other way is to go to Turkish hammam. Do you know Turkish hammam style? So that might be a research starting point to really develop some kind of a.
You have to educate us. What is that? You have to look it up later.
That's a research point. I don't have a solution at this point, but that's also a very power efficient way to take a shower or clean yourself somewhere. So. Okay.
So that's kind of an onboard global supply source, right?
Yeah.
All the circuits will share in it.
Kind of.
The noise and everything.
Yeah.
I was wondering if you've had any issues with metastability, or do you make sure that VAA is high enough to ensure that that doesn't occur towards the detail?
Yeah, I mean, it's all about the design. If you're not careful, obviously you go down too much and you get a metastability situation before it make the decision of that comparator. Obviously, if you are dropping too fast, not careful about the level shifters powering, then obviously you're going to get into metastability. That's why you have this range. Range kind of drops a lot, right? So 1.2 volt, you can go maybe with 10-bit resolution, maybe 0.6 volt with 1.2, which you are boosting to 2.4 volt. And there you don't have really issues with different input ranges. But if your supply drops too much, obviously that is going to affect that decision point and the range that you're going to have. It's going to affect your input range for sure.
So my expertise is in very high speed, and this freaks me out. So let's put that aside. But if you actually, I was wondering if you've studied the noise on this, if you have this, because for instance, in held voltage, your the two currents are fighting noise, right, to win. And that's how you actually start the regenerative process. But now, what is happening is that dynamically, that current is also being decreased.
Decrease, yeah.
And somehow it's kind of, there is this two dynamics. It looks like two loops that are actually going to fight each other.
Because yeah, this node has different junctions, right?
Yes.
And there is a mismatch from here to there, from here to there, here to there on that junction, which is going to also here to there.
And the more this goes down, the higher that sensitivity.
And that became an issue, yeah. It both drops, and they may drop a different way because of the mismatch, and so you have to be careful about that. But again, we are not building a 12-bit ADC.
Yeah, you should be fine.
8-bit or something.
No, I was wondering if you guys have looked into actually characterizing.
We didn't look at that. As long as we get things working, we go for it.
Thank you.
So your tests are under 500 lux, right? Your image was taken under 500 lux.
Yeah.
Of light. Is it calibrated to that
No.
intensity, or because you know if you double it, you're gonna have you can double almost your FPS, and it's gonna bring more harvesting and but also like increase the FPS. So you need to decrease the sampling time in order to have an image, right?
Well, if you increase the light level, your power consumption also increases.
Yeah.
I mean, it's not like, because instead of a lower 8-bit transition, you have all 10-bit transition for your pixels. As a result, your power is going to increase on the ADC side.
But also you're going to be harvesting more.
For sure, yes.
More energy.
But your power consumption is going to increase. We set the 500, which is a standard room lighting condition, that or a little bit brighter.
Yeah.
You end up with maybe 100 to 200 to 500, but even 500 is too much. Like we may have only 100 or in that range.
And is it adaptive? Like when you increase it to 1,000, does it get faster? Is it good, or is it just?
Well, we keep the frame rate the same.
Okay.
So that we can be able to compare the difference, because it's all depends on that timing that we have. Set this timing for 7.4 frame. We have higher frame rates too that we reported, that you can run it at 20 frames per second, but the power consumption is going to increase. Which one has yeah, this doesn't have.
Also, if you keep the same light, you're going to have a darker image, right?
Yeah. Typically, what they report also in image sensor stuff is that they report in the dark. If you report in the dark, your ADC is going to consume less. Your analog signal chain is going to consume less because they are not amplifying the signals. So as a result, you end up with lower power consumption if you report it in the dark. If you report it in room lighting or outside lighting, your power is going to increase. And image sensor companies does that too. So they don't lie, but they don't full disclose also. You have to figure out yourself. That's the issue. And here you can run it at 100 kilosample per second, but your power is going to be 6 microwatts for the supply with ADC. And this is related. So we run the image sensor 54 by 50 at 7.4, which ends up like 20.5 kilosample per second. So that's the power that we use. I can run that imager at maybe 14, 15 frames per second or 30 frames per second, but that's the power that ADC is going to burn. So, and I can run it at 1 frame per second also, which power is going to go from 14 to 5 or something. And at that rate, I can maybe, that's like, I mean, if you calculate this, like 8-second harvesting, 1 second imaging, is this a full disclosure, do you think? Because I'm running for this data assumes that I give and capture 1 image per second. So my frame rate is 1 FPS instead of a 7.4 FPS. So my power consumption is much, much lower than this. 3 or 4 microwatt or so for this, for 1 frame per second. And I probably harvest that much of a power during 8 seconds to be able to run it at one frame. Which again, you can find it in the journal paper.
How much is 500 lux compared to like normal room lighting?
Well, this is probably around 100 right now,
Okay.
which is comfortable. 100 to 200 is okay for studying, reading, and stuff. 500 to 1000 is kind of operation room kind of level. But there, I have, it depends on how you measure. That if you look at this figure, this is the sensor for this lux meter. It looks up, which on top of it, there's a light directly sees it. If I flip it to the other way, my way, it probably reads like 200 or 250 or so. It depends on how you place this. That's why this is there, so that you know where this is looking at. And I can put this one upside down and say that this is 100, and then disclose that way. But that's, again, not a good way to present. Or if you have a mission to teach something to somebody through publications, you have to do this. Otherwise, you do for other reasons, not for training.
I guess I'm curious, why did you use the heat filter for this?
Well, typically, we use the green filter to kind of emulate, because this one has lots of stuff, infrared and stuff. So we don't really cause that infrared to go to different locations to create, or infrared or UV, to create more charge and make sure that a single light is coming through it, and we know exactly what they expect from it. And most of the time, they don't tell you this, but they use the green filter with 10 nanometers for all image sensor specifications. Although they report the full bandwidth, but typically most of the spec are coming at 550 nanometer plus minus 10 nanometer filter, true filter. So it's a habit from industry, so you have to use it. Any other question?
Let's thank our speaker. So we'll be around. Feel free to have more food and, network a little bit more and talk more about the talk. And thanks everybody for coming. Oh, okay. Close. I gotta